the nodes are still the same in symmetric order. First come all the nodes of alpha, then comes this guy, then all the nodes of beta, then comes this guy, then all the nodes of gamma. Same on this side, it's alpha, this, this. But now, notice what's happened. This guy still has gamma. The size of gamma is the Tamari coordinate here, but the Tamari coordinate of this guy is 1 plus the size of beta plus size of gamma, because now that's the size of the right subtree here. So you can see that this operation has increased exactly one of the coordinates of the Tamari coordinates, and it increased it to the smallest possible value. If you took any value smaller than 1 plus beta plus gamma to this guy, it wouldn't satisfy this it would violate this condition. So if I'm going to increase this Tamari coordinate from absolute beta to anything else, it has to be enough to avoid crossing the link from this guy to his children. So basically, by studying this kind of idea, you realize that this is exactly the smallest. This tree is above this one in the Tamari ordering, and there's nothing in between them in the Tamari ordering. And furthermore, all of the coverings are of this kind. So the covering relations are formed that way. Well, now what's happening is that if I flip left and right to take the dual of the operation, then we have different coordinates because now we're counting the size of the left subtrees instead of the size of the right subtrees in the coordinates if I'm flipping left to right. So what must happen is that the operation of on the dual must be taking the dual coordinates, and every time I do a positive rotation, I'm sort of doing a negative rotation on the dual. So the conclusion is that if every covering relation in the Tamari lattice increases the positive coordinates, and in the dual it decreases it because it'll go from something like this to something like this if you flip left and right. Therefore, on the covering relations, the dual of this is less than the dual of this. If this is less than this, so flipping left and right, this is going to be less than this, because flipping left and right also converts this side to this side. That's why I had the theorem that I mentioned a minute ago, that the duality is reversed. So again, this diagram, if I tipped it on its side, the red lines would be in the same position, because what I've done is I put the dual of this guy over here and the dual of this guy over here. These are I worked everything out so that their dual was in the 180-degree rotation in position of the other person. So now there's another thing I wanted to show you about this picture, though, and that is the next theorem, which is why I like this way of representing the force, and that is that if F is related to G in the CRE8 lattice, then F is also related to G in the Tamari lattice. So these lattices aren't independent of each other, but there's a strong connection between them. So what does that mean? Picture-wise, it says that anybody who any relation in the CRE8 lattice also corresponds to the same relation in, like here. This tree has to be less than this one. Well, this tree is less than this one. It isn't directly less than this one, but it's less than this, which is less than this one in the Tamari lattice. And so that's the theorem that relates one to the other. It says that being CRE8 related is a stronger condition than being Tamari related, but they are exactly analogous. That this is a little coarser relation. And this theorem is also obvious because if you look at the covering in the CRE8 lattice, what we've done, if I can only find the picture of the covering in the CRE8 lattice, we've done something that increases the coordinates. Yeah. So if we look at the if we look at the Tamari coordinates, how many descendants everybody has here? This was the guy that has this is the big guy and this is the small guy, and you see that the number of descendants of everybody here is the same, except that all the people on this right path here have gotten more descendants than they had here. So all of the Tamari coordinates of some of these nodes are bigger than they were up here. But inside the rest of the diagram, the Tamari coordinates haven't changed. So by going from here to here, I increase some Tamari coordinates. I don't decrease any Tamari coordinates, and that's why it's less than the other one in Tamari land, because Tamari definition is based on the coordinates entirely. Okay. So now I've got this this idea of Tamari lattice, and I promised you 3 lattices. I'm going to the third one, which is the Stanley lattice. Before I do that, let me just mention, why do we study these things? I mean, you know, the theorems turn out to be rather beautiful when you start looking at them on trees, but so what? And I don't know. Years ago, I wouldn't even have raised that question, because it was, to me, you know, it was so obvious that it's interesting to discuss this stuff that I didn't mention any other justification. But anyway, so some people now think the only purpose of computer science is to make money for other people. So how does this make money for anybody else? And so my answer to that is, well, historically, it's always turned out that whenever there's a clean mathematical relation between fundamental objects that we work with every day, like trees, forests, this turns out to give us more familiarity with those objects. And we study these things. We look at them, and all of a sudden we're more comfortable with trees, and we see bigger pictures. We take giant steps when we start thinking about trees. We're able to envision many more things to do with them. We think of other structures that are built on top of these, and it's because we've gotten some fluency. You know, in the old days, we didn't have the name of what a mathematical concept of a tree was, and neither do we have names for other things that we now use every day, like vectors and fields and lattices. So by studying these properties of these things, especially when they're clean and natural, it always has turned out that this has led to later developments in the next generation. So it's there's another lattice on permutations. It's turned out that it was first discovered by some scientists about 1960. And I did a search for it, and there's been hundreds of papers on this written since then, where people have found all kinds of ways to use that lattice, which is now called the DURHAM lattice. But anyway, there's so many people finding important ideas of this lattice. I've related it to sorting networks and all kinds of things that weren't clear originally why they would be important. But when there's something clean and natural like this, it always seems the history always makes it important. So that's why I think this is cool stuff. Okay, now the Stanley lattice, and here I could instead of using an S, I'm just going to use the ordinary subset notation, because it looks a little bit like an S. And then I can use like, you know, for the opposite relation, I could also say G is related to F like this, you know, and the meet can be written this way, and the join can be written this way. So I have symbols for it. And for Stanley lattice, I'll just use ordinary set symbols, meet, cup, and cap. So anyway, what does this mean? And this says simply that the depth of x in F is less than or equal to the depth of x in G, for all x. In the same, so here we have coordinates of a forest that are different from the Tamari coordinates. The Tamari coordinates, we listed how many descendants everybody had. I don't have another color of pen, so I'm just going to write these. So these are the Tamari coordinates. The Stanley coordinates in this forest are the depth of a node. So A is at depth 0, B is at depth 1, C is at depth 2, D is at depth 3. See what I'm doing? How far down did I go? E is 4, F and G are at 5, H is 1, 2, 3, I is 0, J is 1. Okay? And in the dual I can show its depth too. So J was 0, I is 0, H 1, G is 2. Just write them down 3.
Scratched out, and you can fetch these things apart and then clean out the surface altogether. So I get a really perfect replica of this object, and now I finally understand what is going on. So we have 2 of these interlinked. Could I somehow get 3 of them interlinked? And so I had to think about it for a while, but then it became obvious. Well, if we take a different kind of knife, not kind of, a straight knife that we sort of rotate around the middle of the blade as we go around the torus, but instead, we take a knife like that. So now we have essentially 3 sort of half blades coming together in the middle, and I slowly rotate that knife as I push it forward along the worm of the torus. And going once around the torus, I will make sure that this rotates exactly 360 degrees. It's kind of important to do it that way. And then we get this, and you can see those spiral cuts. And you don't quite know what to expect until you kind of shake it loose. And now we can see we have 3 of those pieces all interlinked. Of course, we can do it with 3 blades. What about if we use 4 blades? We could put them at 90 degrees and add a 4th one. It's the same as basically using 2 cuts with a knife, one going around that way, the other one going around that way. But in either case, we would still turn the whole contraption through a full 360 degrees. So every piece of material winds around the torus and connects back to itself. Well, what would you get? Probably something that has 4 rings. And in order to make it more visible, I gave this one not a round donut shaped cross-section, but I basically made a square cross-section. Its topology is still a torus, just the fact that it has ridges and flat faces doesn't matter. And now, after the cut, yes indeed, we get something that has 4 intertwined rings. You immediately ask, what about 5? What about 6? Well, 6 is a nice one, because now we can start out with a hexagon cross-section, a perfectly regular hexagon. And if we cut a hexagon with 3 diameters, then each one of the pieces is itself a small triangle. And these triangles are perfectly equilateral, so you can see a perfectly equilateral cross-section. And then 6 of those essentially form the hexagon that makes this shape. And by cutting it apart, yeah, we of course get now 6 rings. And that makes an even more intriguing kind of potential sculptures that we might have. And that it makes it even part of the puzzle. That's where I stopped. So now I try to build one of these. Okay, what we've seen before, rotating the knife a full 360 degrees as we go around the donut. Well, if you do it wrong and you rotate your knife only 180 degrees, and what does that do? Now, somehow this doesn't want to come apart here. It still hangs together. It seems to be like one band. Actually, it's a band that goes around the loop twice, and it seems to be somewhat intertwined.
Is it one continuous piece of bread?
It's one continuous piece of bread, so it's a little harder to cram these cream cheese in there. And again, we can look to some sculptures of Keisa Ushio, who has made this kind of shape, but much more beautiful, much more regular. I've exaggerated what he has done in some of his sculptures. And you can see it's basically a donut. You get this one groove that spirals around, that goes to the inside. Now, I really would like to make a really giant sculpture of this. It would be awesome to have a sculpture like that, where you could step inside and see yourself reflected again and again in all the different parts of this inner space. So let's focus on that inner space. What have we taken away from the torus. We have cut something out, and that thing that we have cut out is actually a Mobius band. What's a Mobius band? Oh, let's see. If you take off your belt here, right, and you wrap your belt around, you know, that, in the ordinary way you close your belt, it's just a cylinder. But if we give that belt a 180-degree twist, so the dull side gets to the shiny side and connect it in that way, now we have a Mobius band. And what's special about the Mobius band is that if you start hiking on the shiny side and we go around, suddenly, oops, we're ending up on the other side. So we have stepped from one side of the band to the other without going over the edge. We're just going once around the loop. So that's a Mobius band. Of course, that's a very, very famous structure. But before, I already mentioned that we might want to rotate the knife at different rates. So what happens if you rotate it 3 times as fast? So as it goes around, it swings through 3 times 180 degrees. Then you get this. But now we've taken out a Mobius space that makes flea flips. I call it the triply twisted Mobius space. And I certainly sent pictures of that to Keisa Ushio and then asked him whether he would carve one of those. And so far he hasn't done it yet, but I think one of these days he might come up and create a big stone sculpture that has this particular shape.
It looks like kind of like a propeller or something. So it looks like it should be on the front of a plane.
Yeah, or it could be the head of a tunnel boring machine. Or, what you don't know, this really is the galactic concentrator. Okay, if you hold that in the right spot, it will take the power that comes from the black hole at the center of the galaxy and you focus upon you and it gives you eternal beauty and intelligence and all the good stuff. But don't tell that to anybody else. Yeah, you're the first one that thinks I'm crazy. Now, you were asking, is this any good? And you know, some architects were fascinated by the concept